Okay, our next presentation is a case study taking a combined approach to improve prospectivity modelling. Presenting that for you will be Chris Woodfull, Chairman with SRK Consulting in Asia, Steve Busuttil, Principal Research Geologist with, Geoscientist with BHP, he's joining us remotely, and Vish Avasarala, Founder and CEO of DeepIQ. Welcome.
Just finished the conference. We're going to step away from operations and go back to where it all starts. I'm a geologist with training and experience, but hopefully there's some takeaways for the downstream mining side. So machine learning is a topic which currently attracts a lot of interest in geology, yet results have been somewhat underwhelming according to some. So is it a case closed? It doesn't have applicability in geology, specifically prospectivity analysis, or is it a case of it's early days, and hopefully we'll test the early days scenario here. So while we're only providing an introduction to an exploration case study, I think the topics we touch on today, such as the importance of the quality of the data and the type of data available to us, and the proxies we develop to overcome some of the limitations of the data, and the overarching theme of combining specialist knowledge and the collaborative nature of this study have wider applicability. And I think we've heard that through a few talks across the conference. The quality and quantity of the input data and the associated relationships or criteria defined as part of the input model is a key determinant in how good your output model, i.e. your prospectivity analysis, will be. In geological terms, these relationships or criteria may be more complex or nuanced than can be immediately established from the raw data. Therefore, in addition to a need to clean the data, which is pretty typical for all machine learning exercises, it may make sense to refine or enhance the raw data. This is a particularly pertinent theme we will touch on in this overview. In simple terms, prospectivity analysis is a predictive method typically used at a regional scale to narrow in or focus on and rank prospective areas. Now, prospectivity maps score the ground in terms of relative prospectivity within a grid or a raster. These scores are not probabilities of finding a deposit at a given pixel. Obviously, it's a tool typically used by exploration companies, but it can also be used as a tool for geological surveys as part of land management, inventory or promotional strategies, and it could be used by sophisticated investor organisations as part of their evaluations. In terms of the machine learning workflow, mineral prospectivity analysis, i.e. the model, is an integration function that relates a set of geological features, input variables or evidential maps, to the presence of the targeted mineral deposits, the output variable. As noted earlier, machine learning has attracted a lot of interest, and certainly in geology. And why is this? This is because it promises an objective approach that minimises human bias, as well as the ability to rapidly interrogate large and disparate data sets. We know it's suited to many areas, including medical diagnostics and engineering applications, just to name a couple. From an operational mining perspective, you may be more familiar with some of the time series examples well suited to machine learning, such as truck movements, development meters advanced, bench meters drilled. And it certainly has applicability in evaluating more complex interrelationships in mining, such as ground control monitoring and mining development, be it hard rock or soft rock. An interesting example from a recent conference I attended was longwall shearer control and associated advancement rates. I was also interested to hear yesterday from one of the presentations which included machine learning. It was probably more about processing, but also a focus on mining, that one of the conclusions from that presentation was it requires engineers and data scientists working alongside, i.e. the intersection of engineering and machine learning. And I suggest this is an important takeaway and theme of this talk, albeit geologists and data scientists. So what about geology and geospatial data? Think about the inherent bias that we can get from geological logging or mapping, even with experienced geologists and good mapping and logging systems. In comparison, though, the machine learning process can be subject to other biases that can be attributed to the input data and the defining criteria or their proxies and the feature of interest, such as a copper deposit in the instance we're looking at today. We need to be checking or asking, is the data suitable? Is it clean data? Is there a better way of presenting this data? Is the algorithm appropriate? We can be dealing with lots of data at multiple scales, and the geospatial queries can be computationally complex. However, limited and/or poor data selection, including poor quality data, the complicated relationships we have between the data, and the criteria defining the geological features of interest, such as a porphyry copper deposit target, can be minimised with a nuanced combination of geoscience and data science, i.e. integrating geological knowledge with machine learning. The area of interest we're looking at is a well-explored area in northern Chile. It was a three-staged collaborative study carried out over 12 months. Phase 1 being a proof of concept stage, which focused on cleaning, handling, and utilising a wide array of data available to us to determine preliminary target areas with acceptable confidence levels. And should we meet those criteria, then asking the question, can we improve on this? Phase 2 was a model enhancement stage, which focused on enhancing the quality of prediction through updating the models. And Phase 3 was about target definition, with the aim of generating high-quality drill targets or drill-ready targets, which we could hand over to BHP, and they could look to advance those. An important component of this study and any machine learning process is producing robust input data. So data was ingested to a cloud-based platform. Data cleaning, where required, included cleaning around inconsistent formats, missing attribution, missing values, etc. The robust input data production also included developing a range of new evidential maps, which were derived from the compilation, evaluation, and a reworking of this geoscientific data within a mineral systems framework, i.e. we're considering and recognising the key geological factors controlling the generation and preservation of porphyry copper deposits in the area of interest. In assessing key geoscience-based features for analysis, the SRK team worked closely with Vish and his DeepIQ team, who were very much focused on the data analytics side. This included looking at ways to automate some of the cleaning processes. For example, around data sets affected by anthropic features, human-induced features, or affected by superficial geological features, such as slumping and erosion, which is very prevalent in a rugged terrain. These could bias outputs. So advanced analytics were carried out using DeepIQ's proprietary software, Data Studio, and a series of machine learning models were developed using a range of approaches. And Vish will talk more about this. Importantly, the machine model outputs were reviewed, compared, and iterated. And the review process included comparing to a well-established knowledge-based mineral potential mapping process, initially in 2D using ARC, and then replicated in the Data Studio software. So if we look at this in terms of a prospectivity analysis workflow, what's probably most pertinent is it included a series of mutual feedback loops between the data-driven and the knowledge-driven workflows. And apart from allowing us to ask questions and review results, it's also important to understand and assess what is actually driving those models. And that iteration process and feedback process allowed us to do that. So some of the geological, geophysical and remotely sensed data sets available to the study are noted here. I think what's most pertinent, and it's the recurring theme, or one of the recurring themes, is it included several 2D evidential maps, new additional input data developed for the study, such as a solid geology interpretation, a structural reinterpretation, element ratio plots from the geochemistry, a 2D alteration model or footprint. We're certainly creating proxies from the original raw data. And also there was a range of enhancement processing on the geophysical and topographic data. And related to that theme, a number of these maps were very important in driving the machine learning process. We were also asked to look at developing a 3D geological model. And for this, we also produced some new evidential data sets, such as developing geophysical inversion models and forward modelling analysis to help constrain interpretations at depth. Taking the structural geology and solid geology interpretations, including cover and the intrusion and alteration maps into 3 dimensions. And estimating the thickness for key geological sequences and estimating a preservation horizon, i.e. or depth of formation. So we'll start looking at a few examples of the input data sets. And the ones we're showing here are all newly developed maps from this study. Or we're not showing the whole area of interest, we're just showing a small area. One thing to note was there was only a limited number of training sites in the area of interest, and you have to be careful when you've only got a limited number of training sites that you don't have the modelling driven by just the training sites. By creating additional inputs such as these interpreted geological maps and enhancements of selected geophysical data, rather than just using the original data sources, proved to be very helpful in simplifying the learning problem and producing better machine learning results. For example, I'll just touch on one, even though we've got 3 up there. The structural interpretation not only included analysis from multiple data sources, such as magnetics and published maps, etc. We also attributed the type of structure, major, minor, and also a kinematic history on the structure. Understanding the age of formation and subsequent reactivation across tectonic events, including the important magmatic mineralising events, can identify potentially favourable structural pathways for mineralising fluids. The pertinent structures which are active during mineralisation, and they can help drive the model process as well. 3 more examples, and again, 2 of these, the topographic structure analysis and the alteration patterns, were new input maps. It's interesting to note the EM data. You'll probably notice a corrugation through it. There was certainly a levelling challenge with this data, and that reflected the difficult acquisition conditions across what is a very rugged and elevated terrain. So obviously, we're playing with data that's not always perfect. So in terms of a 3D model, we created a final block model, 200 by 200 by 200 metre resolution, slightly lower than the 2-dimensional resolution, which is around 150 by 150 for 2D. But we integrated still a range of evidential properties and for both the machine learning and also a fuzzy logic approach to targeting. Key elements included distance functions from favourable features such as major structures or granites, alteration, and ultimately the final block model was then ingested into Data Studio for targeting analysis. So we'll just look at a couple of examples from the output data, again from a small area, from the area of interest. And I'll note that sites A to D are a selection of the training sites that were available to the study. So we're showing a fuzzy logic and a machine learning example. What's useful to understand is on the fuzzy logic-based prospectivity model, this is a knowledge-based targeting approach independent of the training data. It is related to the key criteria from the mineral systems approach and a relative weighting established by the geologist. It's a well-established targeting technique, commonly used in areas where few or known deposits are present, with which to train exploration data sets. We developed it in parallel with the machine learning models to complement the machine learning process and the outcomes. On the machine learning side, in the early stages of the pilot study, multiple output models were generated using various combinations of input data to generate the best outputs, regardless of the provenance of the data. In contrast, during phase 2, where we applied deep learning models, these were built using selected data sets. For example, surface input data only, subsurface input data only, or a combination of some surface and subsurface data. Now, while one selected data set model may have provided the best overall results, no models were perfect, each missing a few of the training sites. So from here, the study team started looking at combining different models using a deep learning technique known as fusion to overcome the shortcomings of a single model to see if we could improve on what were good outcomes, already meeting the KPIs that BHP had set us. And Vish will talk more about that, including talking a little bit about fusion. And the best phase 3 machine learning models were based on deep learning. To produce the final model, the best phase 3 models with the fuzzy logic model were used. So while the fuzzy logic was initially providing a complementary pathway, it was actually embedded into the final model process. So we're just touching on the iterative analysis and the relevance of that. So when we look at prospectivity results from a geological knowledge-based perspective, I think there are a few salient points we can initially take away. The output review and iterative analysis approach was integral to the process. It helped create the collaborative environment that we worked in, especially as we were all working through COVID and remotely. We had a team effectively in North America and a team split across Australia. Some of the examples that came out of that iterative process was the surface versus subsurface data sets or proxies for the environments we were considering. Also, bringing the different models in via fusion came out of that iterative process. In essence, it allowed us to collectively better understand the key evidential data sets and layers driving the analysis and the differences across these different models. Interestingly, however, despite the extensive inference network and several iterations, inference network being the wide array of data, the preferred fuzzy logic-based mineral potential model relied on only a few key evidential layers as the main drivers of the outputs. And several of these were the new data sets created by or guided by the geologist, such as subsurface intrusion margins from an interpretation by the geologist, subsurface 2 to 10 kilometre upward continuation of the magnetics which help define intrusions, also enhancement processing and interpretation through the phase of the study, major faults, including northwest trending and north trending transcrustal structures, and near-surface mapped intrusions overlying large bathylitic bodies defined by the interpretation. And a similar set of evidential maps could also be attributed to the machine learning models. While we had a lot of raw data, it was proxies relating to that data which actually drove some really robust model outputs. In comparison also to between machine learning and fuzzy logic, the magnetic alteration evidential layer also helped drive the machine learning modelling outputs. As we touched on earlier, the overall aim was to provide more discrete focus areas for BHP for near-ready or further evaluation. And from 10 broad-scale focus areas, we're talking about excluding training sites within this area of interest. 30 more very discrete focus or near-target areas were defined, and 4 of these were selected by the BHP team for further evaluation. So from BHP's perspective, and I think hopefully Steve will highlight that later on, but certainly from SRK's and DeepIQ's perspective, it was a pretty satisfactory outcome. So as an interim summary from a geologist's perspective, the collaborative approach between SRK and DeepIQ allowed for a powerful cross-fertilisation of ideas and concepts amongst a diverse group of specialists. It wasn't just the data scientists driving a model output with raw data. Certainly the collaboration was also complemented by regular interaction and feedback from the BHP team. Experts in Chile and porphyry copper deposits in Chile. And this was most relevant through the second and third phases of the study. Also notably around the data, it was the higher resolution airborne magnetic data and the enhancements generated from this data, which are very important in generating interpretive data sets that provided the basis for the geological model and evidential layers which help drive, those proxies which help drive the mineral potential mapping. And I think, just to finish off my section, the introduction of deep learning fusion models was instrumental in generating optimal models for the study. As noted, some training sites were not strongly developed in the fuzzy logic or the early machine learning models due to their respective characteristics, or maybe it was a lack of data for them. With the introduction of a fusion modelling technique, some of the important training site deposits were more clearly highlighted and defined. Right, I'll hand over now to Vish to take us through the data-driven analytics side. Hopefully he's online.
Hi Chris, are you able to hear me?
Hey Vish, I'll give you the next slide.
Are you able to hear me?
Yep, there you go.
Yeah, okay, yeah. So, hi everybody, thanks for the time. We are DeepIQ. We're a software company based out of Houston, Texas. Our product DeepIQ is a self-service AI software focused on the industrial world, where subject matter experts like geoscientists can come in and build high-end AI models to do things like prospective analysis or any other use cases that are of interest to them. Next slide. Now, geospatial data analytics is unique and a little challenging, and there are 3 main reasons for that in a nutshell, right? One, the data can occur at different resolutions and can occur in different formats, right? You can have different kinds of file formats. The resolutions can be different. For a same area, you can have one map or data set with 1 million points, and then map with a few thousand points. You have sparse and irregular data, and you have different kinds of noise effects. Converting all that data, combining all the data into an analytic-ready data set is a tedious task. And what DeepIQ's software allows you to do is use drag and drop components to build analytic-ready data sets addressing resolution issues, noise issues, no data issues, and bring high-quality data sets with that. The next issue is structured learning. What I mean by that is, when you look at standard machine learning, every data point, prediction at every data point is independent of prediction of other data points. But in geospatial data sets, you have strong correlation between predictions. If you're predicting a certain location to have high chance of being a prospect, and location just beside it also has a higher chance of being a prospect. So you need to model structural relationships in terms of geospatial proximity and structured learning, particularly when the data sets are not very large, right? If you have 2,000 images where each image has 1 million pixels, that's a much more easy problem. But when you have small areas with limited geospatial data occurring at low resolution, it's a very challenging problem. And we have developed algorithms that work very well on these sparse data sets to do geospatial predictions. And last thing is, when you're doing geospatial data, you typically end up needing to do a lot of geospatial querying, figuring out distances, what is contained in a polygon, what's in the intersection of different polygons and all that. Doing that in an analytics software, to date, there is no self-service aspect to it. So you will end up requiring to write a lot of code. And again, Data Studio allows you to do that using a simple drag and drop software, so that you don't need to write code. You can convert, for example, an image where different rock formations are there in polygon structures into a labeled data set that's ready for machine learning, just through a couple of drag and drop click-throughs. Next slide. Now, the analytic process that we follow for these use cases is the following. First, we take all these data sets that occur at different resolutions and convert them into a Excel-like form data structure that can have millions of data points, but at the end of the day, it's location versus different geospatial properties, and it's a very large big data file on a cloud database somewhere. Once the data is in that clean format, it becomes amenable to machine learning. So it's a clean data set. All of a sudden, you don't have to deal with all these very exotic data structures and maps and polygons and all that. It's just a huge Excel file. That's what machine learning algorithms like to handle, and we create that. And then we allow you to develop machine learning algorithms on top of that. All that is automated through DeepIQ software. Next slide, please. Now, for the problem of interest, what we have first done is pose it as a machine learning problem. We created this nice little data set that combines all these geospatial data sets that Chris talked about, and then we posed it as a machine learning problem where each location needs to be classified, or using segmentation, there are other approaches too, into a region where there is a high likelihood of being a prospect or not. One precaution that we have to take is to make sure that you separate out the training and test data sets geospatially. As you've seen, we train on three different. We divide the whole area into 4 grids. We train on 3 grids, and we predict using that machine learning algorithm on the 4th grid. And hopefully, that prediction covers a lot of the known mines, but it also point out new mines as anomalies, right, as predictions. And then those are the high prospects that are not yet being discovered. If we do it this way, you guard yourself against overtraining that might happen when you distribute the data randomly. And what we evaluated our model is against recall percentage, right? So that the percentage of known mineral occurrences that we are able to predict correctly at a given threshold of the map coverage, right? Assuming we are okay with a certain percentage of map being declared as a prospect, what is the percentage of the mineral occurrence that we are able to cover? That's how we optimize our model performance. Next slide, please. And in terms of machine learning, there are different kinds of algorithms that we can build. The first is a deep learning algorithm. It's a very sophisticated algorithm. It has a lot of variables that need to be trained. It requires quite a bit of training data, but on a wide variety of industry-leading problems, when there's enough training data, this has been shown to have outperformed all other systems. The second is a decision tree algorithm. It's a much simpler model. It still requires training data, but the number of samples are smaller, so you can get away with having smaller training data sets. But on the industry standard problems, when there's a lot of data, deep learning has outperformed decision trees. The final is human interpretable models. The key there is geoscientists might want explainability, right? Deep learning is a black box model. Even decision trees tend to be black box models. If a geoscientist says, I need to look at the prediction and understand why something has been predicted, you have to come up with an explainable model. It turns out AI can also generate formula, human interpretable models, the formulas. So they're in a separate branch called genetic programming, and we'll cover that also in the next few slides. Right. One issue that we have to deal with is to handle sparse data. There's a lot of data sets like geochem that have very few data points spread across the region of interest. And we took two different approaches to handle this. One approach is to interpolate across a very small area around the actual reading, and then use a no data available value for the rest of the map. So most of the data has no data available, except in the region where we have readings, and we interpolate around a small area, so we have a little bit more data. And the hope here is we hope the machine learning algorithm learns to use the data when there are readings available, and learns to ignore the no data values when there is sparsity and there's no data around. So you leave the learning up to the machine learning model and say, learn to ignore when there's no data, right? The other thing that we have done is sparse data is an additional filter. So for example, you build a model without the sparse data as an input, then you treat the sparse data set as an additional model where you have a positive evidence when there is good data at a particular location, and then you apply that as a positive filter on top of your machine learning predictions to filter out regions where there is no evidence from your sparse data set, right? So it's a post-processing filter rather than an input to the machine learning model. We tried both these approaches, and we had fairly comparable results with both algorithms. Next slide. Now, I'll go into a little bit of detail into each of the three different approaches. The first is deep learning. The deep learning algorithms are inspired by the way human brain works. They're biology inspired. They're hierarchical networks where each layer takes a certain inputs, manipulates them, and passes to the layer above them, just like in a human neuron system works. And the output of the final layer is the prediction, right? That you trying to optimize. These algorithms are very deep. There are a lot of parameters, but on a wide variety of problems, including image analysis, speech, text, NLP, natural language processing, they have been found to be the industry-leading performers. Next slide, Tim. Chris. Now, the nice thing about deep learning is the following, right? While the models are very deep, one of the cool things about deep learning is you do not need to do feature engineering. For example, in the below, you see a river image, and you're trying to build a model that identifies the pixels associated with a river. That's a middle purple kind of stream flowing. in a typical machine learning algorithm, if you don't want to use deep learning, you have to calculate a lot of features, thousands or even hundreds of thousands of features that calculate things like color gradients or texture or colors, etc., etc. In deep learning, you leave it to the model. You take the raw image, you feed it to the model. The model intrinsically calculates the feature without you having to engineer anything. And that's the power of deep learning. It takes away a significant amount of engineering that goes into a standard ML algorithms. And that's why they can solve very complex problems where, if not for deep learning, you would have to model millions of interactions between a lot of complex variables and it automatically handles all of that for us. We go to the next slide. So what we ended up doing is we took this very multivariate geospatial data set where each region had multiple geospatial attributes, and we treated that as an image, or in a 3D case as a volume, where instead of an image with the RGB 3 channels, red, green, and blue, you have an image where each pixel has many more channels, each channel being a geospatial feature, whether it's magnetism or alterations or geochem, et cetera, et cetera. And then we pose this as a classification problem, also as a segmentation problem. We use two different approaches and compare both of them. And we train machine learning models deep learning models to predict where there are prospects, right? And we had to do a couple of, we could not use standard run-of-the-mill deep learning models that you can download from the web or are available in open source, mainly because it's not a three-channel image, it's a n-channel image, and also because of the data sparsity and et cetera, we had to tweak the structures of the networks. So once we did that, we basically trained the model from ground up instead of using pre-trained models, and then we made some structural optimizations to existing deep learning models. It's called RASNet. We took that model, we optimized the existing structures, we got pretty good results. What you're seeing here is the recall we got at a 20% map coverage in the area of interest. We got 97% of the known mineral addresses we were able to retrieve at a 20% map coverage. Now, the second is the human interpretable models. Interestingly enough, they are also biology inspired. Instead of where deep learning is inspired by the brain, human interpretable models, genetic programming is inspired by Darwin's theory of evolution. The idea is if each solution is represented as a population, as a member of a population, and you allow population members to interact with each other and reproduce to create new population members, and only the fittest population members are allowed to survive. Eventually, because of the survival of the fittest, after a few generations, the most fit solutions will survive, and that will be an optimal problem to a particular optimal solution to a particular problem. Right. So if you go to the next slide, so in genetic programming, the first thing to do is to basically say that every solution can be expressed as every formula can be expressed as a tree, as you've seen there, right? The formula there can be presented as a hierarchical tree you see on the top, in the middle column. Now you can create little small mutations in the tree to create new formulas. You can take two formulas and swap regions around the formulas to have kind of a reproduction effect. Two formulas combining together to create two new formulas. Once you have that, and then if you let only the fittest formulas survive to the next generation, you iterate, you end up getting better and better formulas that fit a particular problem that you're trying to solve. So these are human interpretive models that can be generated by evolutionary optimization techniques like genetic programming. Next slide, please. Now, in this use case, we had to do a lot of fine-tuning to standard genetic programming approaches, including simplifying the problem structures so that only certain formula shapes are considered, and we had to calculate a bunch of features that are geospatial friendly, like properties from a particular region, like standard deviation, mean of features, etc., etc. And then we evolved formulas, and the formulas, as you see here, we anonymize the formula a little bit to make sure that that the actual formula for this region is not out, but we have been able to get fairly good accuracy in predicting known mineral occurrences. The interesting thing here is while the performance is not as good as deep learning, the formula itself is something that geoscientists can look at and interpret and say, I agree with why this has been declared as a prospect, or I don't agree with it. I want to further fine tune and change parameters and tweak it. Next slide. And the last one is the decision tree. And the decision tree, the idea is the algorithm that we use is a random forest. You train a lot of different trees, each tree on a subset of data, on a subset of the training data. And for the final prediction, you average them out. It has very nice properties. And one interesting property is there are not a lot of hyperparameters to tune, so they're easy to learn and easy to use. And when the data is not very, when we don't have too much data, random forests or even simpler decision trees like CART, etc., can be a good option for us. On this problem, if you look, we use a very similar technique like the deep learning, where we pose it as a classification problem. And if you go to the next slide, we got a reasonable accuracy on these models, not as good as deep learning, but something still in the 90s, right? So these models were outperformed by deep learning models, but if the data sets were much lesser, they could have been a good alternative for us. Next slide, Chris. Now, the one thing that I want to point it out is, Chris talked about fuzzy learning, where knowledge from a geoscientist is encountered as a computational model, right? And now I talked about deriving formulas using AI, and both have their advantages and disadvantages. The advantages of a knowledge engineering approach is you can take the geoscience knowledge and map it, and even if the number of known occurrences are very small, or even if a particular knowledge aspect is not represented by any of the known occurrences, you can still have a good chance of finding finding newer prospects, because the geoscientist is able to still encode that knowledge. However, in a data-driven approach, you will not be able to do it. But a data-driven approach, it's completely automated. A geoscientist does not have to come in and encode all his knowledge. In a fuzzy model, there could be bias because of the limitations of an expert's knowledge, or the limitation of the amount of time that he can spend tweaking this model. On the data side, there's limitation of the bias in the data. The known mineral occurrences could be all in a particular region, or could be attributed to a particular geographical property, and your model may not generalize to learn newer mines, right? Newer prospects that do not satisfy the property. So both have complementary strengths, if you will, and it will be, I think, a very useful tool to combine the strengths of both into a holistic approach. So combine both AI and knowledge to create the best of both worlds. And that's the idea behind Fusion. Next slide, please. Now, Fusion is a very, very big topic in itself, and it's a well-researched topic. The idea is, if you have end decision makers, let's say you have a knowledge-driven model that geoscientists have built, you have an AI-driven model that has been built using existing known occurrences of minerals, and then you bought a mineral prospect map from a third-party vendor who has used its proprietary databases to build one. Now, how do you combine all of this into one decision making? You have two competing approaches, right? Approach one, you can say, I'm going to, all three decision makers need to agree, in which case you will lose a lot of mineral prospects because maybe they do not agree on many regions. Or you can say, even one of them needs to point out something as an occurrence and I will consider occurrence, then you'll have a lot of false positives. Is there a better way to do it? It turns out there's a huge area of research that deals with how to combine different decision makers' decisions in a statistically optimal way to optimize your cost function or your business need, and that can have a very strong impact on combining competing approaches or complementary approaches to create a best of the world output for you. Next slide, please. Now, what I show here is a hierarchical rule for combining decisions, binary decisions, right? So if the topmost box here shows the simplest case where n decision makers, all decision makers are independent, they are similar in terms of their error-making probabilities, and the cost of false positive is the same as cost of false negative. Declaring the minimal occurrence as a nominal occurrence has the same cost of declaring a nominal occurrence as a minimal occurrence. If you assume all these three things, then fusion turns out to be a very simple problem. You can just take a maximum vote and declare the decision as a maximum vote among all the decision makers. But turns out in real world, none of those assumptions hold. And as you go down, the complexity of the fusion algorithm increases. And I think it's out of the scope of this talk here to actually go into the details on how to do fusion in the more complex cases. But the good news is that there are techniques to fuse decision makers. So you supplement, you take the best of each decision maker, and you are able to hide his weaknesses, if you will. Next slide, please. Now, the example here shows how we use fusion to some good effect. So what you see is three different models. The first model we developed on subsurface data. The second model on using surface data and some of subsurface data also. The third model is the knowledge model, the facility model. If you notice, in the first two models, two different known mineral occurrences are missing. In the subsurface, one mineral occurrence was missing because it had no subsurface features in the data we collected. In the second one mineral occurrence was missing because no surface properties were available in that. And it's tough for us to combine all of that into a single machine learning model and have enough control over the learning process to learn both occurrences in the same learning iteration. So when we separate it out into two different learning problems and then use fusion to combine, if you see the final fusion result, you're able to see that all known mineral occurrences have been covered. The accuracy has improved marginally from 97 in deep learning to 97.6. But the good news is all known mineral occurrences have been covered in the final predictions at the threshold, map threshold that PHP wanted. Next slide. So that's the overview of the machine learning algorithms that we implemented. And I'll yield to Steve for the conclusions part.
So over to you,
Hello,
Steve.
can you hear me?
Yes.
Yes, great. Sorry about the technical difficulties before. Look, one point I wanted to make at the start, just to give some context to this whole project, was that BHP Minerals Exploration, which is largely our greenfields exploration arm, found that our application of prospectivity analysis in greenfields context was hampered by the fact that ideal data situations are few and far between. We're always dealing with somewhat incomplete data sets, somewhat sparse data sets, somewhat low quality data sets, and we wanted to bring to bear both geoscience compilation and some advanced machine learning expertise on the problem to help us address the problem at hand, which is how do we create well-constrained prospectivity models given the limitations we have on data in a greenfields context, and particularly in areas where pre-competitive data is not that abundant. So that's a precursor to what the guys have been speaking about, and that was the challenge that was put to both Chris's team and Vish's team. So in terms of what we've learned, I'm going to touch on points that have already been covered, but the first point is we really think there are means by which we can handle sparse and non-uniform data points, and one of them, and I stress is one of them, is a point that that Vish was talking about in terms of how we use sparse data as a confirmatory rather than a mandatory data element or data input. And that realisation meant that we could use data sets that we might have otherwise not used because the data wasn't uniformly sampled or undersampled across the survey area or across the study area. The next point is an important one, and I think one of the most important outcomes of this study was the implementation of Fusion, and it's been discussed by both Chris and Vish. We found that it makes sense to use Fusion given a mineral systems type of set of ideas. We try and build models rather than trying to build one model that tries to represent the full manifestation of the mineral systems that we're trying to target. We build separate models that target specific elements of the mineral systems that we're trying to target and build multiples of those. So for instance, building models that are targeting the near surface expression of, in this case, a porphyry system, and building other models that are targeting more deeper expressions of a porphyry system, and then fusing or combining those together to provide a more robust model, we think, in the outcome. The other big point, I think, is that in these sparse, where data is a premium and where we have to try and get the most out of the data sets that we have and the geological knowledge that we have, we found that synthesizing sparse data inputs into geological proxies was an effective way of using data that otherwise would have been difficult to employ, again, in the modelling with good results. So we're, BHP, happy. We've got some what we think to be geologically realistic outcomes out of this, and we're happy with the fact that that these things are born from a geologically constrained prospectivity analysis that is both using the best data analytical analysis that we can find, as well as bringing to bear all the geological inference that we can. So we think it's an approach that can be used in a lot of scenarios.
Thank you. Thanks, Steve. And if we've got any time for questions, we'll take them. If not, we'll...
Am I on? One that I was quite interested in is the outcomes. You talked about having outcomes that you were happy with and different styles of outcome there. Have you tested them in terms of actually putting some holes into them and actually seeing what your modelling looks like in real life?
It's probably a question for Steve, because they've taken four of the areas. I'm not sure where they've advanced those. We only finished the study a few months ago. So, Steve, has there been any further advancements?
No, we're at an early stage, and I suppose we're comforted by the idea that what we're seeing in the models makes sense geologically, but we haven't got that final test. So watch this space, I suppose, is the answer to that.
And a question around how the project actually came about. How did it happen that these three companies partnered on this project? Was it a BHP-driven initiative to test machine learning with an exploration? How was it born?
That's probably me again. Pretty much, yes. I mean, as I probably would have explained in the intro, we were looking for we were looking for companies that could bring a complementary set of skills, and we felt as though that both the companies who are before you at the moment brought a wide range of skills, probably a wider range of skills than we might have expected in any other single vendor. So we wanted to see what those two different viewpoints and different ways of contributing to their final model would produce, given the impediments that I spoke about earlier. So it was initiated by BHP. We brought these two companies together and asked them to work together, and they've worked very well together.
Okay, and I'm conscious of time. Just one final question. Is there an example of the fitness function used for generating the human-readable prediction function? I don't really understand that question. It sounds like one for Vish.
It sounds like a question for Vish. Is it? You might need to...
So the fitness function is basically based on what percentage of, it's based on the classification error, right? So it's based on the accuracy of prediction. So for each formula, you apply that formula on a selection of data and see what is the accuracy of the formula in predicting not middle prospects currently, and then the remaining areas as not middle prospects, right? So obviously, there's a little bit bias in that some of the unknown regions in the zeros, or things that we think do not have minerals, might actually have minerals. But that's a very small portion, very small percentage, so we ignore that. And that's how we fine-tune the formulas.
Okay, and sorry, at the risk of testing everyone's patience, there is one more question for Steve. Given the comments on mineral systems modelling from a geological context, how much did that influence the data used for the machine learning modelling?
It had an impact on the feature engineering where we needed features. I mean, if we extrapolate from the deep learning side of it, we use understanding of mineral systems to inform how the geological feature sets that were being produced by SRK were constructed. So and how they were combined. So in the fusion idea, we were looking at different aspects of the mineral system to try and combine feature sets that were compatible.
Okay, thanks Steve. Steve, Chris and Vish, thanks very much.
Thanks guys.